This is lesson 4 in chapter 2, and we're going to follow up with some special comments about ionic and covalent molecular compounds. The first thing we want to talk about is the fact that we can actually measure this force of attraction between a cation and an anion. And we use Coulomb's law, which we've known about since the 18th century. And this particular law, remember, a law doesn't do anything, but a law is a description of a pattern or regularity, in this case in the form of a mathematical equation. It's one of these things that we believe to be true everywhere in the universe, even though we've never personally, as human beings, been farther than the moon. We've sent a few satellites out of the solar system, or at least one anyway, and yet we believe this to be true everywhere. We have no reason to doubt it. And scientists who are Christians and scientists who are not believe that this is a universal law. And of course, as Christians, the Christian scientists who are Christians would recognize that this is an example of something that shows the consistency and the orderliness of God everywhere in the universe. That he is the same yesterday, today, and forever, and he is also the same everywhere in the universe. And so his creation reflects that, including this law. Now, this law, first of all, is called an inverse square law, because in the denominator, the distance between the two ions is squared. This means that if you double the distance between the two ions, that the force of attraction is going to be 4 times less. If you triple the distance, it's going to be 9 times less, where 4 is 2 squared and 9 is 3 squared. And of course, if you quadruple the distance, you're going to get 16 times less. It's an inverse square law. Very much like gravity, by the way, which is another inverse square law. Two objects are moved twice as far apart. The force of gravity between them will be 4 times less. 3 times farther apart, 9 times less, and so forth. Also, in order to calculate the charge, you need the number of electrons times the charge of an electron. And you also need the number of protons times the charge of a proton. Of course, a proton has an equal and opposite charge from the electron. Finally, you need your proportionality constant. The proportionality constant is roughly 9 times 10 to the 9th. In other words, it's about 9 billion, which is very, very different from gravity. The proportionality constant in gravity is, 6.67 times 10 to the minus 11th. So you can see that between a positive 9 and a negative 11th, you have a factor of about 10 to the 20th power in difference in magnitude between gravity and the electrostatic charge of attraction between ions. In other words, if we were to say a billion, that would be 10 to the 18th, and then 100 would give us 2 more powers of 10. So 100 billion times stronger is the electrostatic force of attraction than gravity, which is a good thing because when things fall and hit the ground, you don't want atoms or molecules breaking apart. So gravity is a much weaker force than is the force that holds the molecules and crystals and things like that together. By the way, that universal law of gravity would look like this. F equals G, which is that 6.67 times 10 to the minus 11th, and times your mass 1, mass 2 divided by the distance between them squared. Note the similarity between the two equations. They're both inverse square laws. They're both the results of the products of multiplying either the masses together or the charges together to get that force of attraction. But also notice that gravity does not have a force of repulsion, whereas the electrostatic force can be a force of repulsion, which is why we hypothesize that maybe there is an anti-gravity force. And in fact, that anti-gravity force now, that's the wrong word, is perhaps something that is now called dark energy, making up, who knows, 80% of the universe. It's kind of interesting. Up until about 20 years ago, we thought we knew what 95% of the universe was made out of, ordinary matter and energy. Now, with the discovery of an accelerating and expanding universe, and this anti-gravity thing that's causing that acceleration, at least hypothesized dark energy, now we think we only know what 5% of the universe is made out of. Sometimes the Lord, in his humor and majesty, kind of puts us in our place. So, in any case, these ions then, we never talk about an empirical formula, a particle with just an empirical ratio of positive to negative ions. We always talk about it with an empirical formula, like sodium chloride, a 1-to-1 ratio. But that 1-to-1 ratio can be billions and billions of sodiums intermixed with billions and billions of chlorines in a predictable pattern geometrical array called a crystal or a crystal lattice structure. And there are various patterns of crystal lattice structures which we will not talk about in this chapter, but we'll talk about when we spend a couple of days focusing our attention on the state of matter called a solid. Ionic compounds have a tendency to be very, very, very hard solids. They generally have a very, very high melting point. If your table salt begins to melt, that must mean that your kitchen is extremely hot. In fact, that probably means that the earth is in the process of melting down. And of course, you would hate it when that happens. Molecular compounds, when we talk about two elements combined together by a covalent bond, that's a binary, meaning two elements. And this is where you're going to use your prefixes right here. And you need to remember what these prefixes are. And when we use these prefixes like di, tri, tetra, penta, hexa, hepta, octa, nona, deca, that tells us how many atoms of each type are in the formula. And years ago, I had a rather astute student. I remember her name. She became a math teacher. Amy did. She was also the power forward in my girls basketball team that I coached for a bunch of years, and also drove a really, really old Cadillac because it was nice and big and her dad thought she'd be safe. And I got a ride home from her because I didn't own a car. And so after practice, I often got a ride home with Amy as she traveled to her home in South County. Anyway, if the first name goes this way and the second name goes down, in the first name we put the name of the atom. And once again, this arbitrarily just tried to erase everything that I made. So, and we want to have a prefix. Let's fix that. Did it again. So we have our prefix, depending upon the number of atoms in the first element in the compound, but we do not use the prefix mono for the first name. And then we have the name of the atom. When we do go downward for naming the second atom, we have our prefix. And then we have the atom, but we shorten that name. We finish off with ide. So, for example, this compound right here, we only have one nitrogen, so we don't say mononitrogen, we just say nitrogen for the first name. And in the second name, where we're going down, over here we're going down, we have our prefix tri, the element fluorine, but we end with I, nitrogen trifluoride. Or if we come down to this one right here, if we have two nitrogens, dinitrogen, and if we have four oxygens, it's tetraoxide, dinitrogen tetroxide. Sometimes we drop vowels in order for to be able to pronounce it better. You should know how to do that. You might remember your organic chemistry, where we have meth, eth, prop, bute, pent, hex, oct, non, dec, and so forth. The different prefixes for the number of carbons in a straight chain. And we'll spend a whole chapter, of course, in organic chemistry later. But there's also many, many common names. So sometimes I would expect you to know the common name, and even the fact that this technically would be called nitrogen trihydride. And of course, the common name for water is technically dihydrogen monoxide. And you can go online and look up dihydrogen monoxide, and if I remember correctly, someone's created a page saying millions of people over the centuries have, well, at least thousands and thousands of people have died from dihydrogen monoxide overdoses, and you need to worry about this. Well, of course, people drown all the time, tragically, and this is nothing more than water. All right, probably the most important word in chemistry is the word mole, which is the amount of something. Sometimes we think of the word amount to be a volume or a mass. But in chemistry, we're a little bit more precise. Volume is measured in like liters. Mass might be measured in grams, but amount is measured in moles. And it's the amount of atoms you need to get exactly 12 grams of carbon-12. 12.000000 till the cows come home. It's an exact number. It's not rounded off. And it turns out that whether you have smaller particles or bigger particles in mass, 1 mole then turns out to be this many particles all the time. It's like the number dozen is always 12. The number gross is always 144. A ream is always 500. But a mole is always 6.022. I would memorize it to 4 places. That will get you through 99% of the math that you need to do with the mole this year. 6.022 times 10 to the 23rd particles in a mole. Call this Avogadro's number, not to be confused with avocados. Okay? And again, this comes out of the late 18th, early 19th century. And so you should be able to convert grams into moles and moles into grams by using your periodic table. I'm not going to spend a whole lot of time on this. You should be using dimensional analysis when you do your conversion. So here's my dimensional analysis. My moles are going to cancel, giving me with grams. My grams cancel, giving me with moles. But this number here is the molar mass, or the reciprocal of the molar mass, depending upon which way I'm going in my conversion. Of course, once you get a mole of sulfur, that's why we like the word mole, because the molar sulfur is this weighted average of its isotopes, 32 grams. A mole of magnesium will have a mass of its weighted average of its isotopes, 24.3 grams, and so forth. And again, notice your dimensional analysis. Moles cancel, leaving you with grams. Or grams can cancel, leaving you with moles. It's so much easier to use dimensional analysis rather than try to memorize whether you're supposed to multiply or divide by the molar mass to get your answer. This is going to cost some of you points, sadly, all year. And that is that every time you use the periodic table, as a rule of thumb, you should always use at least 4 significant digits for your molar masses. More precisely, always use 1 more significant digit from the periodic table than you need in your calculation. So for example, if you're given 16.5, you know your answer is going to be rounded off to 3 sig digs. So therefore, you should use an extra sig dig for your molar mass from the periodic table. And of course, when you start talking about things bigger than atoms, a mole becomes pretty gigantic. For example, a mole of popcorn kernels that are unpopped would cover the continental United States to a depth of about 9 miles. Or a mole of pennies, if we divided it among all of the people on the planet, or in this case, the example is everybody in the United States, which is approaching maybe 7.8 million. No, I take that back. 370 million. That would allow everybody to pay off the national debt. You can see how old this book is, because thanks to the politicians in recent years, if only we were only down to 11.6 trillion. We are at least 3 times that now. We have blown an awful lot of money in the last several years. So that's our debt, or I should say that's your debt. Too bad, you guys. But you could pay off that debt and everybody in the country would still be a trillionaire. And again, I'm going to let you look over the math problems. If you have any questions, make sure you ask me. Another definition for a mole is to actually use Avogadro's number instead of the molar mass from the periodic table. Though it will be relatively uncommon that you use Avogadro's number. About the only time you'll use that significantly is when we do talk about solids and we try to calculate or learn more about crystalline structures and the distance between particles in an ionic compound and math problems like that. But that won't happen for a number of months. We never use the word molecule or molar mass for ionic compounds. We use formula unit. So NaCl is not a molecular formula. It is a formula unit because it's an empirical ratio. There is not a standalone unit or particle of sodium chloride. And we talk about formula weight. I would prefer formula mass, but formula weight instead of molar mass. So for molecular compounds, we use molar mass, and for ionic compounds, we use formula weight, formula mass. Though you'll hear scientists all the time use molar mass for a mole of any type of substance, ionic or covalent. Again, notice the dimensional analysis, which comes in very handy. It reduces the thinking that you need to do in terms of trying to memorize whether you're supposed to multiply or divide by some number. And then when you get into multi-step calculations, where you might have 3, 4, 5 conversion factors, it makes doing the calculation so much easier. All right. Describing compound formulas. So when we talk about what a compound formula is, oftentimes if we dig something out of the ground or we're working in the lab and we have some mysterious residue, we want to figure out what it is, we need to do a chemical analysis. So some of the tougher math problems in this chapter will be about doing a chemical analysis on something in order to figure out what its empirical formula is, and from that to find out what its molecular formula is. So one of the techniques we often use is to find the percent composition. In other words, if I'm talking about water, what percentage of my water is hydrogen and what percentage is my oxygen? You'll notice, by the way, it makes no difference whether I have a teeny tiny Dixie cup of water, or whether I have a swimming pool of water, or if I have a Michigan lake full of water. The percent composition of water will always be the same. And typically when we talk about percent composition, we are talking about percentage by mass, not percentage by volume, and not percentage by number. Okay? 3 different kinds of percentages we use in chemistry. Percent composition is percentage by mass, which means we need the molar masses, the formula masses from the periodic table. And so you can figure out the empirical formula from the percent composition, and you can also work backwards and find the percent composition based upon the empirical formula. In this particular case, you can see that they're trying to find the percentage of each element, the percent composition, given the formula. And notice, of course, you're dividing by the mass of the entire molecule in each case in order to find your percentage of nitrogen and your percentage of hydrogen. It's always the amount you're interested in divided by the total possible in terms of mass. When I grade your tests, that's a percentage by number. It's the number you got right divided by the total possible number that you could get right, which is the sum of what you got right plus what you got wrong. And here's a little schematic diagram. Some people find this helpful. Some people think it's more complicated than it's worth to try to figure it out. But in any case, you're trying to find the ratio of moles of one atom to moles of the other atom in order to deduce the empirical formula. And that ratio, we always work in terms of moles of atoms. So you have your grams from the periodic table, your percent composition from some diagnostic piece of equipment like a mass spectrometer. Then you take your molar ratio right here, and then from your molar ratio you can get your empirical formula. Empirical simply means the simplest whole number ratio. Again, for hydrogen peroxide, H2O2, the simplest whole number ratio would be HO. And then you'd have to have another piece of information to deduce that you need to double the empirical formula to get the molecular formula. For water, the empirical formula and the molecular formula is identical. You can also calculate the formula given the percentage composition. And for this, we typically pretend that we have 100 grams. If you pretend that you have a 100-gram sample, then if you have 27% of a particular element in that 100-gram sample, then you have 27 grams of it. It makes it easy for you, a little easier for you to do the math problem because you can do that step in your head. However, you can use any number you want. You can use 96.8. You can use 2,436,147. It doesn't matter. You're going to get the same formula when you're done, but it's just going to be messier mathematically. In any case, once you find your moles of each, then you look for the moles that you have that are the smallest. In this case, this is the smallest number of moles of an element that you have. Notice, by the way, that we're not talking about Brinkerhoff hydrogen. We're not talking about Brinkerhoff nitrogen. We're not talking about Brinkerhoff oxygen. We're talking about atoms in a compound, not molecules. So that's why this number is 1, not 2. This is 14, not 28. This is 16, not 32. In any case, once you find your smallest number, you're going to divide all of the numbers by that smallest number. This 0.558 divided by itself gives you a 1, and then you get your other numbers, which become a 9 and a 9 and a 3, and so there is your simplest whole number ratio, your empirical formula. Sometimes it doesn't always work out nice and neatly like that, and you might have a fraction in there like a half or a third, in which case you just multiply the entire formula by 2 or 3. Okay, so I'm going to skip the math part here and come over to, let's see. Here's a nice mass spectrum from a mass spectrometer that shows you the relative percentage of some of the isotopes of bromine that are in a particular compound. This compound is bromobenzene, made out of carbon, hydrogen, and bromine. And the relative peaks show you the percentages, the relative abundance, which can be converted into percentage, of each of the different isotopes, of each of the different atoms, as well as the isotopes of those atoms that you would have in this particular compound. So bromine has a weighted average from the periodic table between 156 and 158, way out here. Here is the mass spectrum of ethanol. And you can see that you get a number of unusual clusters of polyatomic ions when your ethanol gets broken up in a charged environment under a beam of electrons, which is what was used in the example in your book. The one that I used in my lab was renate ions. And you can see you get some very, very unusual polyatomic ions. And again, I have spent many, many hours trying to figure out what clusters of available ions could make each one of these different peaks. So that is mass spectrometry. And that is what I did for 12 summers at the Idaho National Engineering Lab under the auspices of the Department of Energy, United States government. That's the majority of my research experience. Okay. A hydrated compound is a compound that has water molecules attached to it. There are different ways that we can represent this. Here's one of them. You have copper 2 chloride, and then you have 2 water molecules. We keep the water molecules intact because molecularly they stay intact in the copper 2 chloride crystalline lattice structure. That's one way to do it. Another way to do it is CuCl2.2H2O. By the way, when you're going to find the molar mass of this thing, don't multiply because you've got a dot there. That does not mean times 2 water molecules. It means you have to add the molar mass of 2 water molecules, which is roughly 36 grams per mole, to the overall molar mass of the entire substance. 1 copper, 2 chlorines, 4 hydrogens, 2 oxygens. And there are many, many kinds of substances that are hydrates. And you did a lab last year where you took a hydrate, put it in a crucible, heated it up in water, and drove the water away, reducing the mass. And that enabled you to find how many moles of water you lost compared to your moles of your cation and your anion. So that should be a review. By the way, water is not the only molecule that you can find attached to crystalline structures. There are other molecules that are small, like ammonia, like cyanide, CN, that can be attached in crystalline structures as well. And that's in a chapter way towards the end of the book. And with that, I'm going to wrap things up. I thought there was a chart somewhere of some of the hydrated compounds that are available, but right offhand, I don't see it. But there are many, and they are mined out of the ground, and we use them all the time. When your molecule that's interspersed with the ionic compound is water, we say it is hydrated. That concludes Chapter 2, and hopefully you found the review helpful.